Welcome to this section on the inverse of 1 by 1, 2 by 2, and 3 by 3 matrices. In this part, I will present to you some fascinating methods that help you to solve the inverse of matrices easily. Follow me up to the end. Let me start with these general facts. The first fact, only square matrices can have an inverse. Square matrices are those matrices that have equal number of rows and columns. These are 1 by 1 matrices, 2 by 2 matrices, 3 by 3 matrices, and so on. So before going to calculate the inverse, we have to make sure that whether the given matrix is a square matrix or not. The second fact, a square matrix and its inverse have the same order, meaning if a square matrix is 2 by 2, then the order of its inverse is also 2 by 2. If the original matrix is 3 by 3, its inverse is also 3 by 3. The third fact, a square matrix is defined whenever the determinant of that matrix is different from 0. If the determinant of the given square matrix is equal to 0, we can calculate its inverse because inverse of a square matrix is defined if and only if its determinant is not equal to 0. The fourth fact, a square matrix that has an inverse is called non-singular matrix, and a square matrix that doesn't have an inverse is called singular matrix. This is simple categorization of a matrix as singular or non-singular depending on the availability of its inverse. If it has an inverse, it's called non-singular matrix. If it doesn't have an inverse, it is called singular matrix. The fifth fact, the product of a square matrix and its inverse is always equal to the identity matrix. Identity matrix is a square matrix that has ones on the main diagonal and zeros everywhere. If you multiply a 3 by 3 matrix with its inverse, we will find a 3 by 3 identity matrix. This property will help us to check the correctness of the answer we obtained at the end of every inverse calculation, especially if we have any doubt on the steps we went through. Having these facts in mind, let's proceed to calculate the inverse of 1 by 1 matrix. If matrix A equal to this 1 by 1 matrix with an element 4, then the inverse of matrix A equal to this matrix, that's the 1 by 1 matrix, with its element equal to the reciprocal of that single element in the given matrix. The element in the given matrix is 4, so the reciprocal of 4 is 1 over 4. Another example, if matrix B equal to this 1 by 1 matrix, then the inverse of matrix B equal to this matrix, of which its element is determined by taking the reciprocal of that single entry of matrix B. The single entry or element of matrix B is 1 over 7. So the reciprocal of 1 over 7 is 7. As we can see from these two examples, calculating the inverse of 1 by 1 matrix is pretty simple. What we are expected to do is just to take the reciprocal of that single entry in the given matrix. So when we generalize it, the inverse of 1 by 1 matrix with an element x is 1 by 1 matrix with an element 1 over x. In continuing to the inverse of 2 by 2 matrix, if matrix A equal to this 2 by 2 matrix, what is the inverse of matrix A? We have different methods for solving the inverse of 2 by 2 matrices, but what I will introduce you here is the simplest and shortest method for solving the inverse of 2 by 2 matrices. This method looks like this. Inverse of matrix A equal to 1 over the determinant of matrix A times this 2 by 2 matrix. I will explain to you what the matrix looks like later. First, let's see how to determine the determinant of this matrix. The determinant of 2 by 2 matrix is simply the difference of the product of main diagonal elements and the other two elements. That is, the product of main diagonal elements, 4 times 3, minus the product of the remaining two elements, 5 times 2. To find the elements of this matrix, what we have to do is just to switch the main diagonal elements and multiply the remaining two elements by -1, or simply take the opposite of them. That's the opposite of 5 is -5, and the opposite of 2 is -2. So let's simplify the expression. The expression is equal to 1 over 3 times 4 is 12 minus 5 times 2 is 10 times the matrix we found. Again equal to 1 over 12 minus 10 is 2 times the matrix we calculated. This 1 over 2 outside the square bracket multiplies each element of the matrix. That's 1 over 2 times 4 is 2. 1 over 2 times negative 2 is negative 1. 1 over 2 times negative 5 is negative 5 over 2. And 1 over 2 times 3 is 3 over 2. Let me add one more question, but in slightly different form. Given that the inverse of this 2 by 2 matrix is this 2 by 2 matrix, what are the values of x and y? In such questions, what we have to do is we have to calculate the inverse of the matrix, and we have to equate the elements at the corresponding positions of x and y in the calculated inverse matrix to the corresponding elements in the given inverse matrix. First, let's determine the inverse of the matrix. A inverse equal to 1 over the determinant of matrix A times the matrix we will determine by exchanging the main diagonal elements and taking the opposite of the remaining two elements, which is equal to 1 over product of main diagonal elements, that's 6 times x, minus product of the remaining two elements, that's 3 times y. To find the elements of the matrix, let's switch x and 6 and take the opposite of the remaining two elements, that's the opposite of y is negative 1 and the opposite of 3 is negative 3, which is equal to 1 over 6 times x is 6x minus 3 times y is 3y times the matrix we determined. This 1 over 6x minus 3y outside the bracket multiplies each and every element of the matrix. That's 1 over 6x minus 3y times 6 is 6 over 6x minus 3y. 1 over 6x minus 3y times negative 3 is negative 3 over 6x minus 3y. 1 over 6x minus 3y times negative y is negative y over 6x minus 3y. 1 over 6x minus 3y times x is x over 6x minus 3y. The simplified form of this inverse matrix is simply the inverse matrix given above. So to find the value of x, we have to equate the values of row 1, column 1 positions in these two inverse matrices, meaning 6 over 6x minus 3y equal to negative 2. Negative 2 means negative 2 over 1. By multiplying crisscross, we will find 6 times 1 is 6 equal to negative 2 times 6x is negative 12x. Negative 2 times negative 3y is positive 6y. This is our first equation. Again, to find the value of y, we have to equate the values of row 2, column 1 elements in the two inverse matrices, meaning negative y over 6x minus 3y equal to 5 over 3. Multiplying crisscross, we will find negative y times 3 is negative 3y equal to 5 times 6x is 30x minus 5 times 3y is 15y. Let's take negative 51 to the left of equality sign in order to collect like terms, that's negative 3y. When we take negative 15y to the left of equality, it becomes plus 15y equal to 30x. Negative 3y plus 15y is 12y equal to 30x. Dividing both sides of equality by 12 and simplifying the expression, we will find y equal to 5 over 2x. That's our second equation. We can substitute 5 over 2x in place of y in our first equation and solve for x. That is 6 equal to negative 12x plus 6 times y is 5 over 2 times x. This implies 6 equal to negative 12x plus by 2 1 by 2 3. 3 times 5x is 15x. This implies 6 equal to negative 12x plus 15x is 3x. Dividing both sides of equality by 3, we will find x equal to 2. Once we find the value of x, it's simple to solve for y because y equal to 5 over 2x. So y equal to 5 over 2 times the value of x is 2. This implies y equal to 2 cross out by 2, we left with 5. Thus the values of x and y respectively are 2 and 5. In casting forward to the inverse of 3 by 3 matrix, let's consider this example. What is the inverse of matrix A equal to this 3 by 3 matrix? Again, for 3 by 3 matrices, we have different methods for calculating their inverse. What I will show you here is the one that is short and easy to understand. Before proceeding to the steps of calculating the inverse of a given matrix, we have to form an augmented matrix by combining the given matrix and the 3 by 3 identity matrix. How we form the augmented matrix? Just by combining columns of the given 3 by 3 matrix and the 3 by 3 identity matrix, and separating the given matrix and the identity matrix by using this vertical bar. In all the upcoming steps, what we are gonna do is to carry out elementary row operations in a bid to make this left-hand side matrix looks like the right-hand side identity matrix, meaning we have to do row operations step by step to make all these bottom 3 elements and these top 3 elements to 0 and the main diagonal elements to 1. Whatever the row operation we make to this left-hand side matrix, it applies to the corresponding right-hand side matrix. So let's get started. First, let's convert this 3 to 0. To make this 3 to 0, either we have to add negative 3 to it or subtract 3 from it. To get negative 3, we can multiply this 1 by negative 3. So the row operation that help us to convert this 3 to 0 is negative 3 times row 1 plus row 3. Row 1 and row 2 elements will be the same. So let's copy them as they are. Negative 3 times 1 is negative 3. Negative 3 plus 3 is 0. Negative 3 times 0 is 0. 0 plus 1 is 1. Negative 3 times 2 is negative 6. Negative 6 plus 1 is negative 5. Negative 3 times 1 is negative 3. Negative 3 plus 0 is negative 3. Negative 3 times 0 is 0. 0 plus 0 is 0. Negative 3 times 0 is 0. 0 plus 1 is 1. When we move to the second row operation, we can convert either these 2 or this 1 to 0. But what is recommended is to convert this 2 to 0 first, because this operation can't convert the 0 we already formed in row 3 to some other number. To make this 2 to 0, we can add negative 2. If we multiply this 1 by negative 2, we will find negative 2. So the row operation that can convert this 2 to 0 is negative 2 times row 1 plus row 2. Again, row 1 and row 3 elements will be the same, so let's copy them as they are. Negative 2 times 1 is negative 2. Negative 2 plus 2 is 0. Negative 2 times 0 is 0. 0 plus 1 is 1. Negative 2 times 2 is negative 4. Negative 4 plus 1 is negative 3. Negative 2 times 1 is negative 2. Negative 2 plus 0 is negative 2. Negative 2 times 0 is 0. 0 plus 1 is 1. Negative 2 times 0 is 0. 0 plus 0 is 0. The only element that's not converted to 0 at this bottom triangle is this one. To convert this one to 0, we can add negative 1 to it. If we multiply this one by negative, we will find negative 1. So the row operation that converts this one to 0 is negative row 2 plus row 3. We can copy row 1 and row 2 elements as they are. Negative times 0 is 0. 0 plus 0 is 0. Negative times 1 is negative 1. Negative 1 plus 1 is 0. Minus negative 3 is positive 3. Positive 3 plus negative 5 is negative 2. Minus negative 2 is plus 2. Plus 2 plus negative 3 is negative 1. Negative times 1 is negative 1. Negative 1 plus 0 is negative 1. Negative times 0 is 0. 0 plus 1 is 1. When we move to the upper triangle, this element is already 0. So in formulating row operations, we have to take care in order not to convert this 0 to some other number. Now let's find a formula that can convert this 2 to 0. We have negative 3 in row 2 and negative 2 in row 3. That corresponds to this element. So to convert this 2 to 0, we can simply add this negative 2 to it. Thus, the row operation that can convert this 2 to 0 is row 1 plus row 3. Let's copy second and third row elements as they are. 1 plus 0 is 1. 0 plus 0 is 0. 2 plus negative 2 is 0. 1 plus negative 1 is 0. 0 plus negative 1 is negative 1. 0 plus 1 is 1. Finally, let's convert this negative 3 to 0. If we multiply this negative 2 by negative 3 over 2, it will give us 3. 3 plus negative 3 is 0. Thus, the formula that can convert this negative 3 to 0 is negative 3 over 2 times row 3 plus row 2. Row 1 and row 3 elements will be the same. Negative 3 over 2 times 0 is 0. 0 plus 0 is 0. Negative 3 over 2 times 0 is 0. 0 plus 1 is 1. Negative 3 over 2 times negative 2 is 3. 3 plus negative 3 is 0. Negative 3 over 2 times negative 1 is positive 3 over 2. Positive 3 over 2 plus negative 2 is negative 1 over 2. Negative 3 over 2 times negative 1 is 3 over 2. 3 over 2 plus 1 is 5 over 2. Negative 3 over 2 times 1 is negative 3 over 2. Negative 3 over 2 plus 0 is negative 3 over 2. At this stage, all elements other than the main diagonal elements of this left-hand side matrix are zeros. That's what needed. Next, what we are expected to do is to formulate row operations that can convert all main diagonal elements to 1. Row 1 and row 2 elements of the main diagonal lines are 1s, so no change is needed. To convert this negative 2 to 1, we can multiply row 3 by negative 1 over 2. As usual, let's copy row 1 and row 2 elements because we will not make any change on them. Negative 1 over 2 times 0 is 0. Negative 1 over 2 times 0 is again 0. Negative 1 over 2 times negative 2 is 1. Negative 1 over 2 times negative 1 is positive 1 over 2. Negative 1 over 2 times negative 1 is again positive 1 over 2. Negative 1 over 2 times 1 is negative 1 over 2. We have a general formula that matrix A times identity matrix is always equal to identity matrix times inverse of matrix A. We started our calculation by forming augmented matrix of matrix A and identity matrix. At the end of our calculation, we find an augmented matrix formed by identity matrix I and the matrix found by our calculation. That matrix is simply the inverse of matrix A. In order to get used to it, let me add one more question for you. What is the inverse of matrix A equal to this 3 by 3 matrix? Let's start with this augmented matrix of a given matrix and a 3 by 3 identity matrix. Always it's recommended to convert elements other than the main diagonal element to 0 first, because somewhat challenging task is there. This element is already 0, so let's keep as it is. To make this negative 1 0, we can add 1. That one is already here. Hence, the row operation that can convert this negative 1 to 0 is row 1 plus row 2. We can copy row 1 and row 3 elements as they are because we will not make any change on them. 1 plus negative 1 is 0. 0 plus 1 gives us 1. Negative 1 plus 2 equal to 1. 1 plus 0 is 1. 0 plus 1 is again 1. And 0 plus 0 is 0. Next, we have to convert this negative 3 to 0. If we multiply this 1 by 3 and add to it negative 3, it will give us 0. So the row operation that can convert this negative 3 to 0 is 3 times row 1 plus row 3. Again, let's copy row 1 and row 2 elements as they are. 3 times 0 is 0. 0 plus 0 is 0. 3 times 1 is 3. 3 plus negative 3 gives us 0. 3 times 1 is 3. 3 plus 1 is 4. 3 times 1 is again 3. 3 plus 0 is 3. 3 times 1 is again 3. 3 plus 0 is 3. 3 times 0 is 0. 0 plus 1 is 1. Next, let's make this negative 1 0. If we choose this one to add it to this negative 1 in order to make the negative 1 to 0, this 0 will be converted to 1 because its correspondence is 1. Thus, to keep this 0 as it is, we have to use row 3 for row operation at this stage. The formula that can convert this negative 1 to 0 is 4 times row 1 plus row 3. We will not have any change on row 2 and row 3, so let's copy them as they are. 4 times 1 is 4. 4 plus 0 is 4. 4 times 0 is 0. 0 plus 0 is 0. 4 times negative 1 is negative 4. Negative 4 plus 4 is 0. 4 times 1 is 4. 4 plus 3 is 7. 4 times 0 is 0. 0 plus 3 is 3. 4 times 0 is 0. 0 plus 1 is 1. Finally, let's convert this one to 0. Its row 1 correspondence is 0, while its row 3 correspondence is 4. Hence, we have to choose row 3 for making this element 0, because this 0 can't make the element under scrutiny 0. If we multiply this one by negative 4 and add it to this 4, it will become 0. Thus, the elementary row operation that can convert this one to 0 is negative 4 times row 2 plus row 3. No change in row 1 and row 3 elements. Hence, we can copy them as they are. Negative 4 times 0 is 0. 0 plus 0 is 0. Negative 4 times 1 is negative 4. Negative 4 plus 0 is negative 4. Negative 4 times 1 is negative 4. Negative 4 plus 4 is 0. Negative 4 times 1 is negative 4. Negative 4 plus 3 is negative 1. Negative 4 times 1 is negative 4. Negative 4 plus 3 is negative 1. Negative 4 times 0 is 0. 0 plus 1 is 1. Now, we make all elements of this left-hand side matrix other than main diagonal elements 0. What's left is just to make this main diagonal elements 1. To convert this 4 to 1, we have to multiply it by 1 over 4. To convert this negative 4 to 1, we have to multiply it by negative 1 over 4. To convert this 4 to 1, again we have to multiply it by 1 over 4. Multiplying row 1 elements by 1 over 4 gives us 1, 0, 0, 7 over 4, 3 over 4, and 1 over 4. Multiplying row 2 elements by negative 1 over 4 gives us 0, 1, 0, 1 over 4, 1 over 4, and negative 1 over 4. Multiplying row 3 elements by 1 over 4 gives us 0, 0, 1, 3 over 4, 3 over 4, and 1 over 4. At this stage, the identity matrix comes to the left, and the matrix at the right-hand side is the inverse of matrix A. The other method that's used for calculating the inverse of matrices is by using cofactors. The following are the steps that we use to calculate the inverse by using cofactors. First, calculate the cofactors of each and every element in the given matrix. For calculating cofactors, you can refer part 11 of this series. Second, replace every element in the matrix by its cofactor and determine the transpose of a matrix containing the cofactors. For determining the transpose, you can refer part 7 of this series. Third, divide the transpose of cofactors, that's also called the adjoint of the matrix, by the determinant of the matrix. For calculating the determinant of the matrix, you can revisit part 8 to part 10 of this series. The matrix you will find after these steps is the inverse of the given matrix. By this, I conclude this part. Thank you for your attention. Bye-bye.